and we need to move on to the next speaker. It's actually from Shaosui Xu of Space Science Lab, Berkeley. So, Shaosui, are you there, please?
Yes. Hi. I'm Shaosui. I'm a researcher at the Space Science Lab. Let me pull up my slides.
Yeah. And we can continue the discussion in the chat.
Sounds good. Sounds good.
Thank you.
I hope you can see the slides all right.
Yeah.
Good. So today I'm going to talk about the lunar photoelectron yield inferred from ARTEMIS measurements. And this is me and my lovely co-authors. So just a brief introduction and also motivation. What is photoelectron yield? This is the number of emitted photoelectrons per incoming photons. So this is one of the fundamental properties of solid materials. Here, of course, is a lunar surface. And this quantity is not well constrained for photon energies, about roughly 20 eV. And the main motivation for study this quantity is to a better characterization of the lunar surface charging environment. And then the surface potential we know varies dramatically in different plasma environment, and also in response to solar photon fluxes, which varies a lot through the solar cycle, solar rotation, and also solar flares. Especially during the solar flares or some events, the high energy photons are more bright, and then this high energy photoelectron characterization becomes more important. So we will have a better surface charge model if we have the high energy photo emission yield determined. So that's the main motivation for this study. So I will start with a case study, what the lunar photoelectron looks like, and also especially we make the first report of Auger electrons. So if you look at to the right, this is of example. And if we focus on these two panels, which are the energy spectrum for parallel and anti-parallel electrons. Especially for this one, we see a distinctive line at roughly 400 to 500 eV. To see more clearly, if we integrate over this time interval and plot the spectrum for parallel, anti-parallel, and perpendicular separately, you will see this nice peak at 500 for the 500, which is this line here. And this is what we know from theory. These are Auger peaks. What are Auger peaks? These are Auger electrons, which are the photoionization of the inner shell electrons. So they, because of the atomic level processes, this peak actually occur at fixed energies, which is 500 for oxygen atom. So this is a unique feature to unambiguously identify lunar surface photoelectrons. And also, I think this is the first report of oxygen Auger electrons at the moon by ARTEMIS. So this is a case in the magneto-tail lobe. We selected 4 other cases too to study the photoelectron. Yeah. So now that we have the photoelectron spectrum, and then this is the equation to calculate the photoelectron spectrum. If we have the solar spectrum, the yield, and also the probability function. So both the first two are a function of photon energy, and we can get the photon flux from FISM2, which is a solar spectrum model. And then another quantity we need is this probability function, which characterize the distribution of electron flux as a function of photon energy beam at a single photon energy. So this is a function that depends on both the electron energy and also photon energy. Assume all these quantities known, we can calculate the yield with a matrix inversion. And to the right, I show a few different probability functions reported in the literature. And then if we follow that equation and use that probability function, these are the derived yields with different probability function and also for selected photoelectron spectrum. So this is a yield against photon energy. And we also plot the photoelectron yield reported in literature, which come from the experiment results, which are the triangle here, which only goes up to roughly 20 eV. So we can see the yield increase rapidly and peak roughly at 15 eV and then drop down. Without doing any more thing, you will kind of assume it just keep dropping. But our calculation are the red and blues because the lunar surface potential is unknown. We have to bound it with high and low values. These are the red and blue lines. But in general, what we can see is that the yield is roughly 1% for high energies and roughly constant changes with altitude. And then the uncertainty is roughly 1 order of magnitude. So it seems everything is fine. But the big thing with this is all the probability function in the literature are assumed. So there's actually no measurements for the probability function at high energies. So that motivates us to do sensitivity study with delta function to test how much things can change with different probability function. So the conceptually to understand the delta function is that, say, if you have a photon with 20 eV, it can produce many 1 eV electrons versus a couple 10 eV electrons. So naturally, when this ratio of electron energy against photon energy is smaller, you expect a higher yield. That's what you see here. These are different levels of this ratio. Now, alternatively, if this ratio is 1, that gives you the lower bound of the yield. So through this sensitivity study, we can infer a lower bound for the yield roughly 0.1%, but we do see uncertainty over orders of magnitude. And then, of course, in the study, we go into detail, look at different parameters and their impact on the uncertainties. So just to quickly summarize, and we make the first report of Austrian, what did I say? It should be Auger electron observation at the moon by the ARTEMIS spacecraft. And we also infer a lower bound of 10 to the minus 3 in photoelectrons at high energies, but we did discover orders of magnitude uncertainty in yield because the probability function is unknown, which motivate future experiments on lunar sample for better understanding. So yeah, so that's all. And this paper is published in JHR not long ago.
Very nice, thank you.
Thank you.
Yeah, I have a quick question. If you go back to the previous plot, could you explain why high surface potential gives a higher yield versus low surface potential?
That has something to do with the correction to the spacewave potential. It's just the photoelectron spectrum will be different when you correct for the potential. And actually, this one seems to be showing more clearly. This impact is more obvious for low energies, but at high energies, this correction is negligible. So that's where you see the two are roughly agree.
Okay, thank you.